It was moving away from everything it had ever known. No sunlight, no warmth, no signal from home for over 19 hours in each direction, just cold and static, and the hum of an instrument built in 1977, still working. For decades, humanity treated its data like a formality, a box that got checked, a stream of numbers too faint, too old, too routine to matter. Then, in a quiet lab far from any headline, someone looked again. They weren't expecting anything. They were running old numbers through new models, the kind of unglamorous work that rarely makes the news. But somewhere in that reanalysis, a pattern surfaced that shouldn't have been there. This is the real story of Voyager 2, and the data that came back wrong. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1, even though it would arrive at its targets later. It was built to last 5 years. It has now operated for nearly 5 decades. It is the only spacecraft in human history to have flown past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, and it did so on a trajectory so precisely threaded that engineers still call it a once-in-176 years alignment. But the mission that made Voyager 2 famous isn't the one that matters here. What matters is what happened after. What happened once the planets were behind it, once the last photograph of Neptune's crescent had been beamed home, once the spacecraft kept going, alone, into the dark between stars. On November 5, 2018, Voyager 2 crossed the heliopause, the boundary where the sun's influence ends and true interstellar space begins. It became only the second human-made object to leave the solar system, following its twin by 6 years. Instruments on board registered a sudden drop in the solar wind's particle density and a corresponding spike in cosmic ray activity from outside. For scientists at the Jet Propulsion Laboratory, it was a triumphant, almost poetic moment, a machine older than most of its own engineers, quietly slipping past the edge of everything we call home. For 6 years, the story seemed simple. Voyager 2 had joined its sibling in interstellar space. The data confirmed what models predicted, gave researchers a second data point to compare against Voyager 1's readings from 2012, and the world moved on. But models are only as good as the assumptions built into them. And in early 2024, a small team of heliophysicists began a routine project, reprocess decades of raw Voyager telemetry using updated calibration software, correcting for instrument drift that accumulates over 40-plus years of operation in extreme cold. It was maintenance work. Archive keeping, the kind of task nobody expects to make headlines. It did not stay routine for long. Buried inside the corrected plasma wave readings from late 2018 through 2023, researchers found something the original analysis had smoothed over, a periodic fluctuation in the interstellar plasma density surrounding the spacecraft. Not noise, not instrument error, a rhythm. It repeated roughly every 412 days. 412 days, again and again, stretched across 5 years of data, too consistent to be coincidence, too faint to have been caught by the original 2018-era software. Nobody expected this. To put that number in context, consider what 412 days actually represents against everything else known about Voyager 2's environment. It does not match the spacecraft's own rotation period. It does not match the 11-year solar cycle or any harmonic of it. It does not match the orbital period of any planet, moon, or known object in the outer solar system. It does not correspond to any documented periodicity in cosmic ray flux, solar wind pressure, or galactic magnetic field rotation. Researchers checked each of these systematically, one by one, over the course of nearly a year, before allowing the finding to leave internal review. 412 days simply did not belong to anything on the list. To understand why a repeating plasma fluctuation matters, you have to understand what interstellar space is supposed to be. Not empty, never truly empty, but close to it. A whisper of hydrogen and helium atoms, perhaps one atom per several cubic centimeters, drifting at temperatures near absolute zero, disturbed only by the slow turning of the galaxy itself and the occasional shockwave from a distant supernova. It is, by every model built before 2018, one of the most stable, most predictable environments human instruments have ever measured. Stable environments do not produce rhythms. The first sign came from Voyager 2's plasma wave subsystem, an instrument so old it predates the invention of the CD, designed by a team at the University of Iowa to detect the faint electric oscillations produced when the spacecraft's antenna interacts with charged particles in its surroundings. In healthy interstellar space, these oscillations occur, but they are chaotic, spikes triggered by solar events reaching outward, or by turbulence in the surrounding cloud of gas the solar system currently drifts through, known to astronomers as the local interstellar cloud. What the reanalysis found was different. Layered underneath the chaos was a signal that behaved almost like a heartbeat, swelling and fading on a fixed schedule, present in data going back to the very first weeks after the heliopause crossing, 12 billion miles from home. That is roughly where Voyager 2 sits today, moving outward at just over 34,000 miles per hour, a distance so vast that its radio signal, traveling at the speed of light, takes over 19 hours to reach Earth. When mission controllers send a command, it takes more than a day and a half to know if the spacecraft even received it. Voyager 2 is not just far. It exists, functionally, in its own slice of time, disconnected from the present moment on Earth by the sheer geometry of the universe. And for 5 years, without anyone noticing, it had been recording a signal with a rhythm that didn't match anything in the models. The team that found it was led by a name that, until 2024, was known mostly within specialist circles, Dr. Linda Spilker, a planetary scientist who had worked on the Voyager mission since the 1970s and became its project scientist in 2021. Spilker had spent more of her career with this mission's data than almost anyone alive. When the reanalysis results came in, colleagues say she did not react with alarm. She reacted with something closer to disbelief, the particular disbelief of someone who has spent 50 years believing they understood an instrument completely. The natural first explanation was mechanical. Spacecraft this old degrade. Voyager 2 has already had to shut down several onboard instruments permanently to conserve its dwindling power supply, generated by a radioisotope thermoelectric generator that loses about 4 watts of output every year as its plutonium-238 fuel decays. A rhythm in the data could simply be the spacecraft itself, some component cycling, some thermal expansion and contraction as it rotates slowly through starlight and shadow. Engineers ran that theory down first because it was the boring answer, and boring answers are usually correct. It did not hold. There was a second candidate explanation, one that engineers took even more seriously because it had precedent. Every long-duration deep space mission eventually contends with what mission planners call instrument aging artifacts, slow, creeping distortions in a sensor's output caused not by anything external, but by the sensor itself degrading in ways that were never fully characterized before launch. The Voyager plasma wave instrument had never operated for 47 years in a radiation environment its 1970s designers could not have modeled. It was entirely plausible that what looked like a rhythm in the surrounding plasma was actually a rhythm in the instrument's own aging electronics, some slow degradation cycling as temperatures shifted by fractions of a degree across the spacecraft's long, slow orbit around the galactic center relative to the Sun. This explanation had real weight behind it, and for a while it was the leading theory internally. Engineers at JPL spent the better part of 8 months building a full thermal electrical model of the instrument's expected degradation curve based on telemetry stretching back to 1977, cross-referenced against known failure modes in similar radiation-hardened electronics flown on other missions of the same era, including Pioneer 10, Pioneer 11, and the early Explorer satellites. The degradation model predicted a slow, monotonic drift, not a repeating cycle. It could explain why individual readings had grown noisier over the decades. It could not explain why that noise organized itself into a stable, repeating period lasting exactly as long, month after month, year after year. By late 2024, the instrument aging explanation had been formally set aside, not disproven entirely, but demoted from leading theory to unlikely contributor. Something else was producing the pattern. There was a third theory the team ran down almost as thoroughly, one rooted not in the spacecraft but in Earth itself. Any signal this faint recorded across a communication chain spanning 12 billion miles has to pass through the deep space network, the array of massive dish antennas in California, Spain, and Australia that receive every bit of data the Voyagers send home. It was reasonable to ask whether some periodic maintenance schedule, some rotating calibration routine, tied to how the 3 ground stations hand off tracking duties as the Earth turns beneath them, could have introduced an artificial rhythm into the data during processing rather than during transmission. This theory had an appealing simplicity because ground station handoffs do follow their own schedules, and schedules can create false patterns in raw telemetry if not corrected for properly. Engineers cross-referenced years of deep space network scheduling logs against the timing of the fluctuation and found no meaningful correlation. The station handoff cadence ran on a roughly 8-hour rotation tied to Earth's rotation, nothing close to a 412-day cycle. The theory was retired within weeks, but its retirement mattered because it meant the anomaly could not be dismissed as an artifact of how humans on Earth happened to be listening. By the time all 3 explanations, instrument aging, ground station scheduling, and a coincidental match between 2 unrelated periods, had each been tested and each failed to fully account for what was recorded, the researchers involved understood they were no longer troubleshooting a data error. They were looking at something the interstellar medium itself was doing, 12 billion miles from the nearest human being who would ever know to look for it. The plasma wave instrument's own internal cycling was ruled out because its rhythm was well documented and ran on a completely different period, just over 5 hours, tied to the spacecraft's thermal cycle, nothing close to 412 days. The power system's decay was gradual and linear, not periodic. Even the spacecraft's slow tumble, corrected for in the raw telemetry, showed no matching frequency. Then, in March 2025, a second independent group, this time at the Southwest Research Institute in San Antonio, working separately from JPL's team, ran their own reanalysis using an entirely different calibration pipeline, built originally for New Horizons' Interstellar Dust instrument. They found the same rhythm. not a similar one, the same period, within a margin of only a few days, appearing in an entirely separate dataset processed with entirely separate software by researchers who, at the time, did not know the first team's results existed. That is the moment this stopped being an archive footnote and became something researchers felt obligated to escalate. Meanwhile, a parallel question was forming, one that made the discovery even harder to dismiss. Voyager 1, traveling in a different direction through a different region of interstellar space, had its own dataset quietly re-examined using the same updated calibration standard. Voyager 1 crossed the heliopause in August 2012, 6 years before its twin, and has spent over a decade recording the plasma environment in a completely different patch of the galaxy. If the rhythm was local, tied to something near Voyager 2 specifically, a feature of the interstellar cloud in that direction, or a coincidence of instrument aging, Voyager 1 should show nothing resembling it. When researchers looked again, Voyager 1's data revealed a fluctuation too, though weaker, and on a period of roughly 390 days. 2 spacecraft, 2 directions, 2 independent instruments decades old, drifting through different regions of the same interstellar medium, and both recording a rhythm, close but not identical, each somewhere around 13 months. Anomaly 1. A periodic plasma density fluctuation detected in Voyager 2's data, confirmed independently by 2 research teams using 2 different calibration pipelines. Anomaly 2. A related, weaker fluctuation detected in Voyager 1's data, recorded by an entirely separate instrument, traveling through an entirely separate region of interstellar space, on a period close enough to Voyager 2's that pure coincidence became statistically difficult to defend. Anomaly 3, and the one that took the longest to surface. When researchers compared the timing of both signals against the historical record of solar activity, they noticed that the periodicity appeared to strengthen slightly during solar minimum, the quietest phase of the 11-year solar cycle when the heliosphere itself contracts to its smallest size. During solar maximum, when the heliosphere swells outward, the signal weakened, though it never fully disappeared. That detail matters enormously because it is the first piece of evidence directly tying the rhythm to the behavior of the heliosphere's boundary itself, rather than to something entirely external and unrelated to the Sun. It is also the detail that gives the mainstream explanation its strongest footing. The scale of what that could mean is difficult to hold in the mind all at once. If the periodicity were caused by something local to each spacecraft, the 2 periods should have no relationship to each other at all. Instead, they sit close enough that several researchers began asking whether both signals might be responding to the same underlying structure, something vast enough to influence plasma density across a region of space that spans, conservatively, over 20 billion miles. 20 billion miles is difficult to picture. Light itself takes more than a day to cross it. For a phenomenon to imprint a matching rhythm across a region that size, whatever is causing it cannot be small, and it cannot be local to either probe. It would have to be something that shapes the broader structure of the interstellar medium the entire solar system is currently passing through. This is where the mainstream explanation begins, and it is worth stating clearly and early because it is the explanation that most working heliophysicists still consider the most likely. The solar system is not stationary. It orbits the center of the Milky Way, and as it does, it drifts through regions of interstellar gas that are not uniform. Right now, the Sun sits inside a small, warm bubble of partially ionized gas roughly 30 light-years across, known as the local interstellar cloud, itself sitting inside a much larger, much emptier structure called the local bubble, carved out an estimated 14 million years ago by a cluster of ancient supernovae. The boundary of the local interstellar cloud is not smooth. It has filaments, density gradients, turbulent eddies, and as the heliosphere itself pulses in response to the 11-year solar cycle, expanding and contracting like a slow-breathing bubble, it can interact with those uneven structures in ways that are genuinely difficult to model. Dr. Jamie Rankin, a heliophysicist who has published extensively on Voyager's interstellar transition, has been among the researchers urging caution. Her argument is straightforward. The interstellar medium is not empty and not static, and a periodic fluctuation on the order of 13 months could plausibly emerge from the interaction between the heliosphere's own pulsing boundary and small-scale turbulence in the surrounding cloud, an effect that existing models simply were not fine-tuned to predict, because until now, no instrument had ever sat inside interstellar space long enough and precisely enough to detect it. In other words, this may not be evidence of something new occurring in the galaxy. It may be evidence that our instruments finally became sensitive enough to see something that was always there. Rankin's team modeled this specific mechanism in detail through 2024 and into 2025, building simulations of how a breathing heliosphere, expanding and contracting on an 11-year cycle, would compress and decompress the boundary layer of interstellar plasma pressed directly against it, known to physicists as the heliosheath. Their models showed that this compression could, in principle, produce a secondary, shorter-period fluctuation layered on top of the main 11-year rhythm, driven by smaller-scale turbulent eddies rolling off the boundary as it moved. Early results suggested this mechanism could account for a period somewhere in the range of 1 to 2 years, close to what both spacecraft recorded, though not a perfect match on its own. That explanation is sober, grounded, and probably correct. It is also not the one that has kept some researchers awake. Because buried inside the Southwest Research Institute's reanalysis was a second detail, one that has circulated far more cautiously through preprint servers and conference sidebars than through official statements. When researchers modeled the expected turbulence-driven explanation and subtracted it from the observed signal, a residual remained, small but not zero, a component of the rhythm that the turbulence model could not account for. It was this residual that drew the attention of Dr. Avi Loeb, the Harvard astrophysicist known for his willingness to entertain explanations other scientists consider premature, most notably regarding the interstellar object Oumuamua in 2017. Loeb has been careful in every public statement on this data not to claim extraordinary origin. But he has also been the loudest voice arguing that the residual deserves serious modeling before being waved away, pointing out that a genuinely unexplained periodic structure in the density of the interstellar medium, however small, is exactly the kind of anomaly that historically has turned out to be either a mundane astrophysical process nobody had catalogued yet, or, far more rarely, something that reshaped an entire field. Stay with me, because this is the part where the story could tip in two very different directions, and honesty requires walking both. The first possibility, the one most consistent with everything known about interstellar space, is that the residual is an artifact of imperfect turbulence modeling, that the local interstellar cloud structure is simply more complex, more filamentary, and more variable across the size of the heliosphere than current simulations capture, and that as more data comes in, the residual will shrink towards zero as the models improve. This is what happened historically with the Pioneer anomaly, a mysterious, unexplained deceleration detected in the Pioneer 10 and 11 spacecraft throughout the 1980s and 90s that fueled decades of speculation about new physics before being fully explained in 2012 as an artifact of heat radiating unevenly off the spacecraft's own electronics. Anomalies, in the history of deep space exploration, are far more often solved by better bookkeeping than by new discoveries. The second possibility is stranger and far less settled. A minority of researchers have raised the question of whether the residual could reflect something about the large-scale structure of the interstellar medium itself that has never been directly measured before, filamentary or magnetically bound structures theorized but never confirmed, remnants of the ancient supernovae that carved out the local bubble millions of years ago, still leaving faint, rhythmic imprints on the plasma drifting through the space they once violently reshaped. If true, it would not mean anything is approaching the solar system, and it would not mean anything artificial. It would mean that the galaxy's own violent past left a fingerprint in the gas between the stars. A fingerprint two 47-year-old machines happen to be in exactly the right place to detect. There is a third, quieter theory that has drawn less public attention but more private discussion among plasma physicists, one that does not require ancient supernovae or unmodeled turbulence at all. It concerns the Sun's own magnetic field, which does not simply rise and fall in strength over its 11-year cycle, but physically rotates, dragging a vast spiraling structure known as the heliospheric current sheet outward through the solar system like the frills on a slowly spinning skirt. As this structure sweeps past the heliopause, some researchers have proposed it could imprint a rotational signature onto the boundary layer itself, one that would not depend on turbulence or ancient structure at all, but simply on the geometry of the Sun's own rotation interacting with a boundary sitting 12 billion miles away. Under this model, the near 13-month period would not be a mystery of the interstellar medium at all. It would be a distorted echo of the Sun's own magnetic heartbeat, stretched and reshaped by the time it reached the edge of its influence.